안녕하세요. 로데슈바르즈 코리아의 최지홍입니다. 오늘도 이렇게 웨비나로 여러분들을 다시 찾아뵙게 됐습니다. 반갑습니다. 네, 오늘 제목 보신 것처럼 오늘 말씀드릴 웨비나 주제는 5G, 그 중에서도 NTN이라고 불리는 부분입니다. 우리 항상 지금 5G 핸드폰들을 다들 쓰시고 계시잖아요. 우리가 보통 스마트폰 데이터 통신을 위해서 5G 통신을 쓰고 있다라고 이제 다들 인식을 하고 계실 텐데, 오늘 말씀드릴 이 5G NTN이라고 하는 부분은 5G가 개발이 되고 상용화가 되면서 그 발전 경로상에서 우리가 다시 한번 볼 수 있게 되는 또 다른 형태의 통신 진화라고 얘기할 수 있을 것 같습니다. 5G 자체가 2019년도에 우리나라에서 상용화 되었을 때를 생각해 보면, 그때 당시에 나왔던 기술 부분은 우리가 보통 3GPP라고 하는 곳에서 나온 릴리즈 15라고 하는 규격을 통해서 5G가 개발이 되었고 시작이 되었다라고 이야기를 합니다. 오늘 말씀드리게 될 5G NTN은 이 릴리즈 15 규격이 계속 발전하면서 릴리즈 16, 릴리즈 17로 계속 진화를 하고 있는 거고요. 그 진화 과정에서 5G가 좀 뭐라고 할까요? 궁극적인 통신이라고 해야 될까요? 그런 지향점을 향해서 움직이는 모습을 볼 수 있는 그런 부분 중에 하나가 될 것 같습니다. 오늘 메인 동영상에서도 아마 같이 보시게 될 텐데, 이 3GPP 이동통신이라고 하는 곳에서 이야기하고 있던 궁극적인 목표는 전 지구를 하나의 통신망으로 묶어서 어떤 통신 서비스를 제공을 하는 이런 부분들을 놓고 항상 그 목표로 삼아왔던 부분들이 있었습니다. 그런데 사실 그렇게 되지는 않았었죠. 여러분들 이미 다들 아시고 계시는 것처럼 이런 목표는 3G 때, 즉 WCDMA 생각해보면 2000년대 초반이 되겠죠. 그때부터 이미 언급이 되었었던 어떤 목표 중에 하나였었는데, 실제로 우리가 기억해보면 3G를 사용을 했었을 때에도 우리 해외 나가면 전부 다 로밍을 해야 됐었고, 우리가 쓰던 핸드폰을 동일한 어떤 기지국과 어떤 동일한 기술로 계속 연결을 시킨다든지 이런 부분에서 잘 안 되는 부분도 있었을 뿐더러, 또 한 가지 말씀드리면 정말 서비스 자체가 안 되는 것도 있었거든요. 예를 들자면 해상이라든지 혹은 비행기라든지 이런 부분들은 우리가 쓰고 있는 이동통신 기술로는 목표는 잡았었습니다만은 실제 서비스를 제공할 수 없었던 영역이었던 것도 맞습니다. 이런 현상들은 사실 LTE 때도 마찬가지로 계속 이어져 왔었던 부분이 되는데, 이제 5G는 그 부분을 실제로 현실로 만들기 위해서 정말 새로운 부분들을 고민을 하고 고려를 하고 있는 거고요. 그런 면에서 나오는 부분이 오늘 말씀드릴 5G NTN이라고 하는 주제, Non-Terrestrial Networks이라고 부르는 이런 부분으로 실제 현실로 이루어지는 그런 과정이라고 보실 수 있을 것 같아요. 5G 기술은 길게 보자면 앞으로 보통 이제 현재 목표는 2030년을 이야기를 합니다만은 6G로 이어지는 어떤 교두보를 마련을 하는 부분도 분명히 있을 거예요. 그리고 그런 면에서 오늘 말씀드리게 되는 5G NTN, 결론부터 말씀드리면 위성을 활용을 하게 되는데, 이 위성을 활용을 하는 통신 연결 방식이 현재 오늘 메인 파트에서도 뒤쪽에서 말씀을 드릴 예정입니다만은 6G에서 도입을 하게 되는 여러 다양한 기술들 중에서 예상되는 기술이 되겠죠. 이런 부분에서 큰 부분을 차지하는 어떤 메인 필러라고 부르게 되는 이런 부분들로 언급이 되고 있는, 예상이 되고 있는 이런 기술이라고 생각을 하신다면은, 현재 나오고 있는 이 5G NTN이 비록 초창기라고 이야기를 할지라도 앞으로 또 다른 모습으로 진화를 해가고 6G로 이어지는 그런 모습들을 우리가 기대할 수 있지 않을까, 이렇게 생각을 합니다. 사실 저희가 이렇게 웨비나를 토크IT를 통해서 진행하는 경우가 좀 꽤 많았었죠. 오늘은 저 혼자 나와서 말씀을 드리게 되었어요. 저도 사실 필드 어플리케이션 엔지니어로 기술 지원을 담당을 했었고, 그때 제가 맡았던 이제 메인 지원 파트가 이 핸드폰 이동통신 관련된 기술 지원을 제가 실제로 지원을 했었습니다. 그래서 그러한 백그라운드에서 지금 오늘 내용은 제가 직접 말씀을 드리고 여러분과 함께 동영상 이후에 메인 라이브 Q&A까지 진행을 하게 될 것 같습니다. 오늘 준비된 동영상은 저희 로데슈바르즈 독일 본사에서 글로벌로 진행을 했던 동영상을 이제 국내에서 보실 수 있도록 자막으로 저희가 준비를 한 내용이에요. 그래서 여러분들께서 아마 보시고 이해하시는데 어떤 무리가 되거나 좀 어려운 부분은 없을 것 같습니다. 먼저 말씀드려야 될 부분은 오늘 동영상에서는 사실 어떻게 보면 좀 개론적인 부분을 말씀드린다고 보시는 게 맞을 것 같아요. 이 5G NTN이라고 하는 기술 자체도 사실 그 내용으로 말씀드리려면 정말 굉장히 방대한 양이기 때문에 오늘 말씀드리는 내용은 기술 개요 성격으로 여러분께서 이해를 해주시는 게 좋을 것 같고요. 물론 라이브 Q&A를 통해서 여러분께 저희가 알고 있는 이런 다양한 부분들을 최대한 전달을 해드리도록 노력하겠습니다만은 일단 내용상으로는 정말 어떤 규격이라든지 혹은 기술의 세부 사항들을 다 다루기에는 시간이 너무 부족합니다. 그래서 여러분들께서 이 점은 먼저 좀 양해를 해주시면 정말 고마울 것 같고요. 만약에 혹시라도 이런 부분들이 충족이 되지 않거나 또 혹은 좀 더 깊은 내용들이 필요하시다, 그런 부분들이 있으실 경우에는 추후에 저희 로데슈바르즈 코리아에 내용을 문의를 해주시거나 코멘트를 남겨주시면 또 그에 대해서 또 저희가 확인해드리고 회신드려서 어떤 부분들을 저희가 같이 논의해 볼 수 있는 이런 기회가 또 되지 않을까 생각을 합니다. 네, 오늘 준비된 동영상이 약 50분 조금 넘습니다. 그래서 지금 시간이 벌써 4시 5분이네요. 이 부분들 이어서 쭉 함께 보시고요. 그 이후에 다시 한번 여러분들 쭉 채팅을 통해서 또 질문들을 올려주실 텐데 이런 질문 내용들을 함께 보면서 이야기 나눌 수 있도록 하겠습니다. 지금부터는 메인 동영상을 함께 보시겠습니다.
Hello and welcome to today's webinar, 5G Non-Terrestrial Networks Takes Flight. My name is Rainer Stuhlfahrt and I'm a technology manager with Rohde & Schwarz. And it's my great pleasure today to guide you through some technology aspects of 5G non-terrestrial networks. So what's my plan for today's webinar? First, a quick introductions and motivations, use cases. Then we'll take a close and brief look into the commercial new space satellite constellations. And the real fun part begins with some architecture aspects. So to introduce the 5G non-terrestrial network architecture, followed by some challenges. As we all know, there is no free lunch. So that also non-terrestrial network introduction comes with some technical challenges into the 5G aspects. I'll just try to highlight a few of them. And we'll also take a look into the protocol world and the procedures coming together with 5G non-terrestrial network. And I want to close this webinar with a brief outlook into the next evolutionary aspects of 5G non-terrestrial network. So let's start. And I hope I keep it entertaining and also interesting for you to listen. So the first quick motivation and the introduction with 5G non-terrestrial network. And I'd like to start here with, I call it my marketing slide, to see this evolution from the world industries. And what we see with non-terrestrial network is that we see a convergence between two ecosystems, the wireless, the communication ecosystem, and on the other side we see the aerospace. Yeah. So both ecosystems will join forces and drive and push the evolution for non-terrestrial networks. So we see it already in some kind of press releases, some alliances between industry players. There are chipset vendors, infrastructure vendors, satellite operators. There are the aerospace, the rocket launch, etc., etc. So this is the whole community is pushing. And also we see a kind of time-wise evolution of 5G non-terrestrial network. With release 17, 3GPP introduced NTN as part of the 3GPP 5G technology. Yeah. And I always say it is a technology enabling. So here the word says enable. That means we keep 5G as a system and we enable non-terrestrial network. In the long-term perspective, even with an outlook on 6G, we understand some kind of unified network, three-dimensional network. So the satellite-based communication will become a part of the network from its inception already. So that is a technology evolution. And I'd like to go further into a first big picture. Yeah, so like the holistic view of 5G non-terrestrial network. Apologies for this nice overview picture as it contains many, many details, but not worries. I don't want to go in all the details. And I more or less have two central pivotal messages with this image. The first message is that 5G NTN is much, much more than just satellite communication. And the second message I have is that with 5G NTN, we have a very long technology development and deployment. Yeah, so it's not like a feature that you realize and you implement and then from there it's done. So it will be more like a long lasting technology evolution. In some further details, for example, when we look into the satellite constellations, 5G non-terrestrial network includes all possible satellite orbit constellations, low Earth orbit, medium Earth orbit, but also geostationary orbits. Yeah, of course, there are some priorities. But besides satellites, we also envisage the possibility to have kind of airborne base stations, so airborne stations, like this acronym here, HAPS. Yeah, that's a crazy term, sorry. High altitude platform system, whatever it is. So that means we have network nodes in helicopters, in drones, in balloons, in airplanes, in stratospheric planes, whatever else in your mind. We have various deployment modes for 5G non-terrestrial network. One can be, for example, like here, that we use satellite-based NTN as a backhaul. So to connect a terrestrial base station via the satellite link to the remainder of the core network. We have the different types of user equipment, like a smartphone, the traditional, that is one of the objectives, to communicate with a smartphone to the satellite, yeah, for basic communication services. But also we describe in 3GP the so-called VSAT, very small aperture terminal. So here the idea is that we have a UE that has at least a higher transmit power, potentially. It is definitively UE with a much more sophisticated antenna performance, so like a higher antenna gain, for example, thanks to phased array antenna beamforming methodologies, yeah, and also operating in a higher frequency range with wider bandwidth. And in the first glimpse, those type of VSAT devices, they can be either stationary, so like a CPE on a building, or they can be maybe based in vehicles, etc. Beside the non-terrestrial network communication, there are also various additional facets. I will not delve further into them in today's webinar, but just for completeness. For example, we have here the communication so-called air to ground. So with terrestrial base stations, antenna arrays with beamforming, we can consider the passengers in an airplane as the kind of users of internet services, and then with beamforming methodologies we provide internet access to the passengers of an airplane, so this air to ground. But also another part is like this air traffic control. Yeah, so Roland Trust, for example, we're also in the air traffic control business, and here it's called as UAV, so the drones, the unmanned aerial vehicles, and there will be some methodologies to guide these UAVs via 5G signals. For example, the 5G network transmits air traffic control commands via a 5G traffic channels or via 5G positioning methodologies like the observed time difference of arrival, like the GNSS support, etc. Such a UAV can, for example, fly on a pre-configured route. Yeah, so all these are additional aspects. Just coming back to my initial statement that 5G NTN is much more than just communication over satellite. So let's have a further details. We distinguish between two facets of 5G NTN, so use cases. One is this new radio NTN. So here the continuation, let's say, of the eMBB, enhanced mobile broadband. So internet access, ubiquitous communication wherever we are. And the UE types are the smartphones or the VSAT type of devices. A second facet is this IoT NTN, so Internet of Things. Yeah, and with that we continue the trend that we started with these IoT technologies. For example, narrowband IoT that is quite famous. But now the difference is that we provide worldwide ubiquitous coverage. Yeah. And the use cases are the typical IoT use cases. For example, we consider it like a best effort quality of service. We consider a sporadic data transmission, a long-lasting battery time. So energy power saving methodologies are highly required here. Yeah? And these are all the second facet. So sporadic data, low traffic, bursted behavior, etc. With the various use cases of 5G non-terrestrial network, we see here a plethora of use cases. And maybe I start to comment that image with a nice statistics I found from the global view from the market side. Sorry, I admit I'm not the biggest fan of statistics, yeah, but I loved that numbers. And there was a statistics from the organizations of operators worldwide, and this statistic stated in 21 we have coverage of about 80% of the human population worldwide. Yeah, so 80%. That means there's still 20% potential customers for future communication services. And the second statistic said we have coverage of less than 40% of the land mass on the globe. Yeah, so be aware, we have the globe and we all know 70% is ocean, maritime zones, and the remainder 30%, and only 40% of this land mass. This is where we have coverage. And that is one of the major motivation. We want to provide ubiquitous services, so internet access wherever we are, in rural areas, in remote areas, so like a ship, container ship, all the logistics, the freight control, the airplanes, the maritime ranges, the mountain ranges, the desert areas, but also cities. Yeah? For example, resilient network, that if there is a network outage, for example, power outage, a very big topic is this PPDR, so this public protection disaster relief, yeah, so that we consider communication as an essential necessity, yeah, and we want to regain and recover communication services after such cataclysm situations in a very fast and very early stage, yeah. And beside this, of course, the goal is and objective is to provide internet services. So either service continuity, for example, from terrestrial into the maritime region where it's unfeasible to build terrestrial base stations. Yeah, we have service ubiquity, so that's internet access all over the planet, but also service scalability. For example, what we know from television broadcast, as an example, that we do the broadcasts, televisions like DVB-S signal, and standards over a certain region, a continent, because that is the very most efficient one to deliver one content to a large number of users. Yeah, and the same will also happen to the wireless world. For example, a software update for a huge number of devices. Yeah, so some information like warning information, like general weather forecast, the political news, the sport events, etc. So such things like that, an operator can also now to discuss about how to scale the traffic to become more efficient in the entire system. Beside 5G non-terrestrial network, of course, we know that we are not the only ones who want to use the space. We see also a plethora of so-called new space satellite constellations. Here, just a quick reminder. I think the most prominent one is Starlink, SpaceX. There are others like OneWeb, like Kuiper. There's Inmarsat, SES, etc. satellite companies driving that. So these satellite constellations are either already in place, in operation, or they will deploy. And I do not want to say that there's a kind of competition. Yeah, in that way, of course, there's a certain capacity needed in future. And by the way, none of those satellite constellations would have the overall capacity to fulfill all these customer requirements. So 5G is going to complement, yeah, and to be together. And we have to see how we can converge and use the services to bring internet access to all over. Yeah. The differences with 5G is that 5G is considered as an entire system. So there's an architecture, there's a quality of service management, there's terrestrial and non-terrestrial links are possible. So it's a whole infrastructure, yeah, and not only just looking at the satellite connections. But we should be aware that those constellations are there. They are also technology drivers. They're pushing ideas, yeah, and we have to cooperate and to see how we can share the whole ecosystem. Now let's take a closer look into the architecture of 5G non-terrestrial network. And with the first slide, I would like to start the discussion on frequency. As frequency is always, of course, the essential part for every communication link, we need spectrum. Yeah, and 3GPP took the decision just recently and to launch 2 new bands and these two bands are possible to be used for non-terrestrial network. It is those two bands, N255 and N256. You see they operate in the L and the S band. Historically, they were coming from a very old, let's say, ITU spectrum, discussed already in the early 90s, when I remember when UMTS 3G was on the horizon. We already had the idea of a future public land mobile network containing satellite communication, and spectrum chunks have been already reserved for that. And now 3GPP takes some of these spectrum chunks, and we have these two new frequency bands, and you see here in the table all the details. The frequencies used for non-terrestrial network operate in FDD, frequency division duplex, so uplink and downlink on two different frequency channels. Also in the potential higher frequency bands, this is due to the long delay. Then also we have to, and maybe as a preface statement, I'm not going to compare the data rate with 5G NTN compared to the data rate with a terrestrial network. From the bandwidth discussion, for example, we see that these two bands, we have a maximum channel bandwidth of 20 megahertz. Remember, for example, in many of the FR1 frequency bands, we can go up to a bandwidth of maximum 100 megahertz. So there is always a kind of difference in data rate discussions. And this is not the focus for 5G non-terrestrial network. So it's not the idea to overtake the speed of the terrestrial network. It is a complement. It is bring communication services into those areas where terrestrial communication has not been possible in the past. And this is the first goal. There will be also future frequency aspects. For example, discussion is in the Ka band, so 17 to 20 gigahertz, 27 to 30 gigahertz, the uplink and downlink bands. We also discuss potentially in the next future the FR3 frequency range, for example, between 7 and 24 gigahertz, the Ku band, which is used today by some of these new space satellite constellations. So there's, like we know, there's this endless discussion about frequency. These two bands, L and S band, are the first ones. And then, of course, we will contribute and we will deliver additional frequency bands in future. With these satellite constellations, in release 17, priority there are two kind of orbit constellations in the primary phase, which is the geostationary and the LEO, the low Earth orbit satellites. So you see here the numbers from the orbit height. Two possible satellite behaviors with respect to beam forming are possible. So there are satellites that are able to steer the beam, and now the satellite can keep the beam footprint kind of static with respect to the Earth surface. So as long as the satellite travels, the beam footprint is kind of kept static. Or the other possibility is that the satellite has a kind of static beam and the beam footprint is moving with respect to the Earth surface. So these both satellite constellations are possible. And this goes together with the architecture. Also in the architecture aspects, we see a kind of technology evolution. In the first deployment phase, release 17, 3GPP considers this so-called transparent payload architecture. So what does that mean? That means the following. So we have here the user equipment, starting from the left to the right. I have a satellite here, the spaceborne station, a ground terrestrial gateway, and the G-node B. That means from protocol world, the communication occurs between the user equipment and the terrestrial G-node B. So always use this analogy. Like today, let's say you see line of sight, the antenna of the base station on the tower. And now with NTN, I'm grabbing the antenna of the base station and I'm stretching it over the gateway up to the sky, the satellite, and then back to Earth. So this is this non-terrestrial payload in transparent payload architecture. So the protocol stack G-node B, and then we have the NG interfaces to the remainder of the core network, the user plane, the access management functions, etc., and potentially also an external data network. With respect to the protocol architecture, we see here how that behaves. So the physical layer terminates in the terrestrial G-node B. So that was also visible in this figure before. So the so-called serving link and the feeder link have the identical radio waveform, the identical 5G radio technologies. So we consider the gateway and the satellite node as a kind of relay in between. Of course, they have very important functions. Also the gateway, for example, for satellite operations, for satellite steering, etc. But from the perspective of 5G, the gateway and the satellite are kind of transparent, are kind of, just a relay. Advantage is with the quality of service concept with such mechanisms, we have our sophisticated quality of service management in 5G. You know this network slicing, the radio bearer concept, the NGU tunnels, the user plane tunnels, all inheriting certain kind of quality of service flows and parameters. This is something we keep. So we have an end-to-end connection, so-called described here as a quality of service flow between the user equipment on the left and the user plane functions in the 5G core network on the right side. And each of these quality of service flow owns a certain kind of profile. So guaranteed bit ratio, throughput, error ratio, what is the latency effect, what is the priority level, etc., etc. So all these parameters are described and discussed and negotiated on a bilateral basis for each of these quality of service flow. With respect to testing, test and measurement, for example, if I consider now such a, and I want to avoid this term base station in that way, but it's coming from the traditional, so base station RF testing. But now, as you see, the term base station consists of, in fact, 3 different entities. We have the satellite node, we have the terrestrial gateway, and we have the G node B, so the baseband part. So all these 3 entities together, they are building this formerly known term base station. And the question is now when we do about RF testing. For sure, for example, there will be testing in the transmitter side, TX tests, like the usual suspects. Power, modulation quality, EVM, spectrum, adjacent channel spectrum, spurious emission masks, spectrum emission masks, etc., etc. And then also we have receiver testing, starting with receiver sensitivity. So if I lower my voice, so then you would stop hearing and listening something. Then we have a maximum input power, but we also have more sophisticated receiver performance tests. For example, an interferer in the adjacent channel or a blocking, an interferer in an unwanted channel far away, but with much higher power. And such constellations we need to emulate in that case. The challenge is, in 3GPP, the criterion for the receiver sensitivity testing is based on today, for example, based on a throughput. So we send a fixed reference channel, we measure the block error rate, and then we calculate the throughput, and the condition is passed if under certain interfering situations, for example, the receiver is able to achieve a number of, let's say, 95% of the achievable throughput. If this is given, then your test is passed. But now we see here in the graph that the throughput calculation, the block error rate, happens between the physical and the MAC layer, where I can do the CRC check on the transportation block. And this is the possibility to determine the block error rate. So that means the terrestrial G node B is the entity that is able to deliver the throughput, while the satellite is, let's say, the front end and containing the RF interface and receiving from the RF side, potentially also with antenna arrays. So that's an option that we put the entire system then in an anechoic chamber, full anechoic chamber, and do the same test in an over-the-air scenario. With respect to 5G non-terrestrial network, so we have here different facets, and I just have a kind of reminder to the 5G network architecture. So we have here all the core network. In 5G, for example, we remember from the core network, everything is based on the so-called service-based architecture. So we have a core network function. That's what we see here in all the F at the end of the acronyms. An access and mobility function, a user plane functions, an authentication function. So that means we describe the jobs, the work that need to be done as a function. And this function offers its service to the other functions. So it's a kind of cloud-based architecture. So the function itself can be executed at various entities in our hardware chain. So it can be inside the core network, inside an external cloud, inside somewhere bringing closer to the antenna, this multi-access edge computing, etc., etc. So we have a cloud-based architecture. SBA service-based. Yeah, and in the first deployment with 5G non-terrestrial network, the radio access network, the RAN, is considered to be independent and parallel. So we have a terrestrial RAN and we have a non-terrestrial RAN. They can belong to the same operator or they can belong to different operators. Of course, we also envisage some kind of mobility scenario between both. So now what are now the next steps with the introduction of NTN and also in the future evolution? The next step is that we try to push and move more of this service-based architecture into the radio access network. So also following some trends like, for example, these open RAN initiatives. Yeah, so like the idea. So that we have disaggregated radio access network components. We have additional interfaces. And also now we bring more intelligence into the radio access network. For example, this MEC, multi-access edge computing. So like a data cloud, data storage closer to the antenna. That we take more processing power. So scheduling decisions closer to the antenna, an autarky of the radio access nodes. For example, that a G node B satellite-based can provide connectivity even without having a direct connections to the core network. Yeah, so kind of standalone reaction times and more onboard processing. Also the introductions of artificial intelligence methodologies for self-control, process control. And this is, let's say, one of the horizons on the technology evolution. Yeah, and even up to some ideas, for example, that I have as data storage, a UE cloud. Yeah, so for some kind of general data, then I can put this data storage inside the UE. What are now the next steps? So first I introduced this transparent architecture where the satellite is a kind of relay and serving and feeder link are identical. In a longer term view, then 3GPP will integrate this so-called regenerative payload architecture. And with the regenerative architecture, now we understand that the satellite itself will incorporate the entire G node B functionality. Yeah, so the G node B with all the physical PDCP, MAC layer, RLC layer, etc. All these protocol layers will be incorporated inside the satellite node. And we have then a core network connections via the feeder link gateway to the remainder of the core network. Yeah? So this is on a longer term view. And this introduction of the regenerative mode will then also come aligned with the possibility of having inter-satellite links, so that one satellite communicates with another satellite. And I just have depicted here a kind of image, a so-called Walker diagram from the architecture. So we have satellites on a descending route, on an ascending route. Then we call this plus, like this character plus. Yeah. So one satellite is maybe connected to the satellite to the right or to the left and to the satellite in front and behind. Yeah. So like this character plus. So we have kind of inter-satellite link constellations. But the challenge is that many of these ISL will not be permanent. So that we also need a kind of dynamic. Yeah, that an ISL inter-satellite link can be established dynamically, can be stopped dynamically, and then we have to reroute the connections. And you see here, this can be really mess situations, and we will need sophisticated artificial intelligence methodologies for that. Then, as I said in the introductions, there's no free lunch, so we have to consider also some challenges. For example, what comes with the radio frequency? The most obvious one, and I think that's it's clear in 5G NTN, is the large delay. Due to the distance, satellite to Earth, we will always have a delay. Yeah, and we cannot accelerate speed of light. For example, in a geostationary satellite, just the delay from speed of light is given as 544 milliseconds. Yeah. But what is even worse is not just the absolute delay, it's also kind of time variant delay or delay depending on the exact position. For example, here, when we talk about the beam footprint, just from the geometry, the satellite steers multiple beams onto the ground. So we have multiple beam footprints, and typically such a beam footprint will have an elliptical shape. And the size of this elliptical shape depends on the elevation angle. A second impact, for example, is here the UE that is in the center of the beam footprint, so-called nadir position of the satellite, and the second UE that is at the edge position of the beam footprint. And just from the geometry here, from the triangle, from the geometry, we see that we have different round trip times. So you can see that this is, of course, a challenge for the buffer management inside the satellite. The second perspective is the round trip time from the view and perspective of the user equipment, the UE. So I always use the analogy like sunrise and sunset. The UE on the Earth sees the satellite appearing above a certain elevation angle on the horizon. So then the satellite gets accessible. Now the satellite is the longest distance. A little bit later, the satellite is perpendicular. So then we have the shortest round trip time. And sometimes later, the satellite is disappearing at the horizon again. So then we have the longest round trip time again. So like here, the green color, we will observe a kind of time variant round trip time over the connection is a satellite NTN. And in combination with round trip time, we also have a change of the carrier frequency, also known as Doppler effect, Doppler shift. Yeah. And the same situation like here, like sunrise and sunset, this in Doppler terms changes into the situation of an approaching transmitter and then into a leaving transmitter. So we have this S-curve behavior of a Doppler shift that we also need to discuss. Another impact, for example, is from the terrestrial world. Typically, we use a linear polarization of the antennas. I remember the times when I had my cell phone and the antenna was there to pull out. Yeah, probably some of you remember those times. Today we have the antenna integrated in the box of the smartphone itself, but typically maybe it's like a linear polarized or like this character X, like the horizontal and vertical polarization. The same for the base station. When we look into the atmosphere, yeah, because satellite is in the atmosphere, in the orbit, here in the atmosphere we have this total electron count, a large number of electrons, and the satellite is moving, and this causes an effect that is in the academy known as the Faraday rotation. Yeah, Mr. Faraday, he recognized this effect, that it means we have a rotation of the polarization. So consequences is possibly that with the satellite connections, a circular polarization, so like shown here as a vector that rotates in the speed, yeah, this circular polarization is probably better protected compared as a linear polarization. Yeah. So coming to all such of these challenges, now with perspective of test and measurement, we will also observe certain kind of challenges into the test and measurement world. Yeah. For example, there will be the two facets, protocol testing and RF testing. Yeah. First, in a user equipment as a DOT, I can do the tests in conducted or over the air. Yeah. So like a full anechoic chamber. Rodenschwarz, we provide such chambers, by the way. Yeah. Then the UE needs satellite services, GNSS, to estimate its terrestrial position. Yeah, so then in the potential setup, we may need a signal generator that is capable to emulate GNSS signals. We need, of course, a mobile radio tester to set up the connections to the UE, yeah, with the fading profiles and the time delay emulation. And then potentially you want to do transmitter tests, not only the usual suspects like power, like modulation quality, adjacent channels, and spectrum emission mask, but potentially also you want to do spurious emissions. So then you need a spectrum analyzer that can look into the frequency range far beyond our carrier. And also we look into the receiver sensitivity testing. So starting from the carrier sensitivity, but also looking into beyond, like receiver performance testing, like intermodulation resistance, like blocking resistance, etc. And in such a case, you potentially need then additional interfering emulations, which could be the job for a signal generator. Yeah. And in the long-term view, also 3GPP will need to tackle the protocol aspects. Yeah, so all these kind of protocol features like the round-trip time, the timers, the mobility scenario, terrestrial, non-terrestrial, etc., that will require some kind of signaling testing as well. So with this, I hand over to these protocol aspects to also understand such of these changed in the protocol procedure. My first message is that with 5G non-terrestrial network, it is much more than just a physical layer. Yeah, so all the protocol layers in 5G need to tackle the aspects of non-terrestrial network. Yeah, we discussed already intensively the physical layer. Yeah, so the delay, the Doppler shift, the Faraday rotation, and also interesting that 3GPP decided to stay and keep OFDMA as the waveform. As I said, we want to enable non-terrestrial network, but we want to keep the impact on the 5G system as low as possible. The MAC layer mainly needs to deal with this long round trip time. So we need a kind of update of the HARC procedure. I'm coming back to this. Yeah. Then potentially also the radio link control, the RLC layer. Potentially we also need some updates of the existing timers just to compensate this long round trip time. With security aspects, then we need to discuss about what is the authentication to satellite-based networks. Yeah? Quality of service, for example, 3GPP introduces new quality of service profiles that tolerate such a long round-trip time. Yeah, so that could be even a case into the decision on your user application that you select on your smartphone, potentially an application, and you're connected over satellite. And now you get a kind of warning. So I'm just guessing, but maybe you get then a kind of warning that there is a long round trip time and maybe this will have a negative impact on your application. Yeah, so like mobile gaming over NTN is maybe not the let's see. Yeah. And even we have potentially new applications on the user plane. With the signaling protocols on the radio resource control, we definitively have an impact on the mobility scenarios. Yeah. For example, the beam from the satellite, so inter-beam management, satellite to satellite handover, also satellite to terrestrial network handovers. Yeah, I'm coming back to this. And also the non-access stratum. The mobility management is impacted by the introduction of non-terrestrial network. Because, for example, with NTN, it is more or less impossible to stop the transmission across the country border. That means now we have network coverage across the country border. Yeah. Theoretically, it's possible that you are in your particular country and you receive the signal and the identity of a network operator from another continent, by the way. Yeah. So that is in theory possible. So now we also need some international regulation and also, negotiations across the operators and spectrum management. What is possible? What is allowed? For example, is a satellite allowed to transmit a signal when it is above a certain country? Yeah. Now let's go into some details. Round trip time. Round trip time affects the HARC operation. And here's just a reminder, what is this HARC operation? So I start with the transmission of a transport block. It will take some delay, propagation time, sure. It is received at the receiver side. We have some additional processing. Then we have a reaction time. The receiver, in my example, I'm using a negative acknowledgement. So I'm sending a NAC. I don't hear. Please send again. So the NAC is transmit. Also again, processing, propagation time, and then the retransmissions. So this is the overall round trip time. So the T-HARC. With the introduction of satellites, of course, you can guess we have much longer round trip times. Here you can see some numbers. As I said, for example, for GEO satellite, this can go up to 600 milliseconds, so including the processing time. This is way too much for the existing HARC operation. In LEO satellites, we estimate a typical round trip time of about 50 milliseconds. And now the agreement is in 3GPP, how can we tackle this? There are various possibilities. One possibility, for example, is I can disable the HARC at all. So that means the retransmission and the reliability is shifted to higher protocol layers, like the RLC layer, the PDCP layer, or even the TCP IP application layer. Yeah. Another possibility is to extend the number of HARC operations. So 3GPP, for example, agreed to 32 HARC processors in LEO constellation, or a third possibility is a kind of automatic retransmissions. So like a transmitter repeating several times the transport block, also to improve the efficiency in terms of, the path attenuation. Another aspect, of course, is the timing advance. And here's just a reminder to general and for the 5G experts as you are, there's no surprise. So the timing advance is a mechanism by the base station to compensate the different delay times. Yeah, so one UE that is in my vicinity, another UE that is at the cell edge. So we have different propagation times, even in a terrestrial network, and they will be individually controlled to make sure all the uplink signal arrives time aligned at the base station antenna. Yeah, so that's the objective of the timing advance. What is the consequence with the introduction of non-terrestrial network, as we have a very large propagation time? The consequence is that we also have a very large range of timing advance values. Yeah, and now we have different kind of aspects, and I just try to present a little bit the discussions in the communities. For example, here situation is the satellite, and there's a very long round trip time to the beam center. Yeah, but also the round trip time is even much longer depending on the position of the UE within that footprint. So that leads to the conclusion that we kind of need a two-step procedure for adjusting the round trip time. Two-step means the network can signal a kind of cell common timing advance as a kind of basis, the common timing advance for the entire use in the entire cell. And then we add an individual UE specific timing advance offset onto that cell common. Yeah, so that is the first decision. The second decision is how can we tackle the long timing advance? And in the first part here in the upper picture, an unalignment timing advance will lead to a very large range of the timing advance in the UE, user equipment side. That's one option. A possible countermeasure to compensate this would be that the base station, for example, defines a deliberate unalignment between uplink and downlink. Yeah, so my analogy is like the different time zones on the globe. Yeah, for example, I live in Central European time. Yeah, and for example, the people in the East Coast in the United States or people in Asia, you have your local time zone. Yeah, so from space, we see the different time zones on the globe. Yeah, so 12 o'clock in one time zone is not 12 o'clock in another time zone. And that could be something like a feature in a base station that I have a kind of frame offset between the uplink and downlink. Yeah. So that is possible. And now you can see here this complex formula, how 3GPP tackles the entire timing advance with NTN. So there's this NTA, this is the individual timing advance command. So like, come closer, please go further away. So like, yeah, please update your timing advance. This is this permanent closed loop control. Then we have a timing advance. For example, I start with that one. That is the user equipment estimated timing advance. So the UE knows its terrestrial position. The UE has an information about the satellite ephemeris. And based on this, the UE does a pre-calculation of the potential distance. And this will lead to a concluded pre-offset of the timing advance. The network can signal, optionally, a common specific timing advance for the entire cell. And in addition to this, we can also signal a kind of network offset. And this network offset would be if the network goes for this second choice. If there is an offset unaligned between uplink and downlink, this can be found in this timing advance offset, to compensate. But also this timing alignment has an effect, for example, into the scheduling period. Yeah, for example, here on the terrestrial, we have a scheduling parameter, this timer K2. Yeah, so you receive the downlink message, the DCI in downlink, and this allows to transmit, for example, in the uplink, the PUSCH. But there's a timing advance. That means the push, PUSCH, is shifted in advance. If there is a long round trip time, and this is in the bottom side, if there's a long round trip time, in the worst case consequence, this PUSCH is shifted towards the received DCI, and in the worst case, the UE would need to transmit the PUSCH even before it has received the grant, the permission, which is not possible. So in that way, we need to defer the transmission of the PUSCH for later compared to terrestrial, and that leads to the introduction of an additional timer, so-called car offset. And this timer car offset allows from the network to configure to defer the scheduling time. And also, in more details, another timer that can be optionally scheduled is this timer KMAC. And this would be a timer in a network to schedule an unalignment between uplink and downlink. Yeah, so if the network has the strategy in a satellite to have a time shift between the uplink and downlink frames in the FDD mode, then the network can signal this time shift by using this parameter KMAC. As I said before, there's also an impact on the mobility scenarios. For example, here we have the mobility of cell selections, mobility inside a satellite from one beam to the other another beam satellite. Then we also have a procedure from one satellite to the other satellite. And even in the longer term view, we also talk about mobility scenarios like carrier aggregations, dual connectivity, seamless handover between terrestrial and non-terrestrial networks. Just as an example that we also need some changes on that. Yeah, because of the introduction of non-terrestrial network, the vision of a handover is slightly different. I start here in the upper left part here. That is a typical handover on a terrestrial view. Yeah, so terrestrial base station, and what you measure is the power level, the RSRP, and I'm close to my original serving cell. The serving cell power is quite high. The neighbor cell power is very low because it's far away. And now you see that vehicle. I'm now leaving the serving cell. What happens is, of course, declinement of the serving cell power and an increase of the neighbor cell power. That's why we call this character X. Yeah. So typically the operator defines here a threshold, a handover trigger. So when the new target cell, the neighbor cell, becomes that many dB stronger than the existing serving cell, this is now the trigger for the handover. So far, so nice. This is proven since many years. But now let's take a base station in a satellite. Yeah, so UE, I have visibility to one satellite. I see also a second satellite, but the major contribution is the free space path loss. Yeah, so the RSRP is mainly triggered by the free space path loss. So from a UE perspective, the distance to the two satellites is more or less kind of identical. Yeah, it's not that much different. Yeah, that means the power level, the RSRP, is maybe not the best choice as a criterion for selecting the best cell when we want to define what is the best cell. So now we have certain solutions and mediums for that. And one famous solution is this introductions of the conditional handover. Yeah, so just as one example, what such a condition could be. For example, the network operator defines the beam center as a reference location, and the handover condition is now the offset in position to this reference location. And if the UE, in this case a vehicle, is a certain distance apart of the reference location, that is now the trigger for the handover. Yeah? Another example to conclude, for example, is that with introduction of non-terrestrial network, this also has an impact on the non-access stratum. I mentioned it already, this cross-country border coverage. And another impact, for example, is the tracking area code. And to keep the signaling low for tracking area code, the idea is to have a kind of Earth static tracking area code signaling. So when a satellite travels above a certain region, it will keep the tracking area code signaling constant. And this is possible because we know in 5G we have the possibilities via system information to broadcast multiple tracking area codes in parallel. And with this, I'm coming to the end of my presentations. But not the final end. I still have a couple of more slides, and I want to introduce a little bit what I stated before, that 5G non-terrestrial network will be a long-lasting technology evolution, and just as an outlook that there's of course a technology evolutions on the path to 6G. Yeah. So for example, when we talk about 6G, we have some buzzwords, for example, like a three-dimensional network, 3D network. What does that mean? That means we incorporate all types of base stations, ranging from indoor small cells, macro cells, high power, high tower antennas for large terrestrial areas, but also incorporating any kind of airborne objects like drones, balloons, helicopters, etc. And then all kind of satellite constellations, low Earth orbit, geostationary orbits. So we have completely 3 dimensions in our networks. We are leaving the way from the cellular world. That means we have satellite nodes that can travel with different velocity versus each other. That means we have a dynamic. in the network. So a cell birth and cell death situations that needs to be tackled. We need to reorganize our handover relationship. We need to reorganize the scheduling mechanisms. So that means introducing a kind of artificial intelligence, self-control in the network, a kind of autarky. Yeah? The network needs to stay resilient even if there's no connections to a kind of core network remainder. Yeah? So that will be the technology steps we have to face and to solve in the next couple of years on this path to 6G. So here just a few highlights. For example, I mentioned the cell burst death situations, network autarky, unified network. That is, for example, also one of the buzzwords like network of the networks. Yeah, that we have different radio technologies that we offer, yeah, and we select the best radio technologies depending on the use case. Yeah, lot of control mechanisms, joint communication and sensing is a topic. Yeah, but also to talk about optical link for free space optical links for this inter-satellite. Yeah, and just as one example, what is more details, when we talk about this network of the networks, I have here this kind of vision of a multi-radio access technology. Yeah, so leaving a little bit the trend. In 5G and LTE, we introduced OFDMA on the radio signal as a waveform. Yeah, very flexible and to have the sub-carrier spacing. With 5G, we made OFDMA more flexible. Yeah, so there's different numerologies, the sub-carrier spacings, the symbol time, the 5G numerology. So this is a flexible OFDMA concept. And now maybe in a longer outlook on 6G, a possibility could be that we have multiple radio technologies depending on the use cases. For example, my 6G smartphone communicates with a terrestrial base station using the FR1 frequency ranges. And then, for example, we can conclude with OFDMA because that is an improved system. Then maybe the smartphone has an additional link at the higher frequencies, terahertz communication, for example, with a very large bandwidth, like, for example, 8 gigahertz bandwidth. And then we may choose a single carrier modulation scheme with pencil beams, but only short time slot, but a wide bandwidth. And a lesson I learned from, for example, my colleagues who are dealing with the television standards, for example, with digital video broadcast, we had different standards, DVB-T for terrestrial video. We had DVB-H for handheld. It never took off, but also we have DVB-S for satellite. Yeah, so we adapted the waveform behavior, for example, with the single carrier, a Rolo factor. We changed the modulation scheme from a quadratic QAM up to a kind of circular, this 32 QAM amplitude modulation aspect. So these are some methodologies introduced for satellite connectivity. Yeah, and that is, let's say, just one potential vision of this network of the networks concept. And with this, for example, I will now just place the 5G non-terrestrial network evolution into our list of different research areas in 6G, where we, for example, have here NTN in the concept of these new network topologies. Beside that, of course, we see all the different aspects of our 6G research fields. Yeah, I will not delve into details like terahertz communications, a millimeter wave, joint communication and sensing, where we kind of combine radar and communications for two facets, artificial intelligence methodologies for various aspects. We have these reconfigurable intelligent surfaces to change the radio channel behavior. Photonics and visible light communication is a huge research field. Of course, we have these new waveforms already discussed in 5G, and we're still continuing filter bank multi-carrier, single carrier frequencies, non-orthogonal waveforms, etc., etc. Yeah? Massive MIMO beamforming, full duplex operation, transmit and receive on the same channel at the same time, but also, for example, new security concepts like a SIM-free operation, authentication mechanisms based on, for example, blockchain methods. Yeah, and with this, for example, we also see that new network topologies are part of this entire 6G research field. Yeah, and with this, I'm coming to the end of my today's presentations. I'll leave you with this slide. It contains additional links for additional materials, like a new white paper that we published on 5G non-terrestrial network. And with that, I'm coming to the end of my presentation. It has been a great pleasure to present. I hope I kept it informative and enjoyable. And thank you for your time, and thanks for listening.
서두에 말씀드렸던 것처럼 5G NTN은 이제 시작 단계라고 말씀드릴 수 있을 것 같고요. 그런 면에서 뭐 지금 단계는 정말 초기 단계, 뭐 이렇게 생각을 할 수 있을 것 같습니다. 대부분의 어떤 기술들은 항상 그렇듯이 초기 단계에서는 아주 작은 걸로 시작을 하지만 이제 점점점 이 영역을 넓혀가면서 확장이 되는 모습들을 볼 수 있는데, 아마 그런 면에서 5G NTN도 우리가 고민을 해보고 좀 주의 깊게 볼 수 있는 부분이 아닐까, 뭐 이렇게 생각이 됩니다. 시간이 좀 많이 지나긴 했어요. 이게 동영상이 길다 보니까 좀 길어졌는데, 일단 최대한 오늘 답변 드릴 수 있는 부분들, Q&A 올려주신 부분들을 좀 말씀을 드리려고 합니다. 우선 시작하기 전에 먼저 말씀드릴 부분은 여기 봉성함님께서 문의를 주셨는데, 발표 자료에 대해서 문의를 주셨어요. 예, 발표 자료는 저희가 공유를 해드릴 거고요. 저희 로데슈바르즈 코리아 홈페이지를 통해서 저희가 확인을 하실 수 있도록 제공을 해드립니다. 오늘 참석하신 분들께는 저희가 추후에 이 링크가 완성이 됐을 때 다시 보기 안내와 함께 메일을 발송을 해드릴 거고요. 다시 보기 페이지를 통해서 자료도 함께 다운로드 받으실 수 있도록 저희가 링크를 제공을 해드리기 때문에 이런 부분들 참조를 해주시면 좋을 것 같고요. 네, 여기까지가 일단 Q&A로 채팅창으로 올려주신 내용입니다. 제가 지금 말씀드렸지만은 지금 시간에 좀 쫓겨가지고 좀 빠르게 말씀을 드렸어요. 그래서 듣기에 어떠셨을지 모르겠습니다만 좀 양해를 부탁을 드리고요. 오늘 말씀드린 이런 부분들은 정말 초기 단계에서 제가 컨셉추얼한 부분들을 설명을 드리면서 어떤 부분들이 고민이 되어야 되냐, 이런 부분들을 말씀을 드렸던 것 같습니다. 그래서 이런 부분 면에서 앞으로 어떤 기술들이 어떻게 또 접목이 되고 실제 이런 부분들이 상용화되는 과정은 어떻게 진행이 되는지, 이런 부분들도 여러분께서 한번 흥미롭게 지켜보실 수 있는 부분이 될 것 같고요. 저희 로데슈바르즈는 그런 면에서 어떤 이런 실제 단말이나 네트워크 장비와 같은 부분들을 구현하기 위한 그런 실질적인 계측 솔루션, 측정 솔루션들을 공급해드리는 입장으로서 그런 부분 실현이 될 수 있도록 저희가 최선을 다해 여러분과 함께하는 어떤 솔루션 프로바이더의 역할을 계속 이어나가도록 하겠습니다. 오늘 뭐 긴 시간, 뭐 1시간이 벌써 훌쩍 지나갔는데 이런 내용들 길게 또 함께 해주셔서 다시 한번 감사드리고요. 다시 한번 말씀드립니다만은 저희 이 다시 보기와 발표 자료에 대한 부분들은 저희가 추후에 또 이메일로 알려드리도록 하고요. 혹시라도 추가적으로 궁금하신 부분이나 요청사항들이 있으시면 말씀드린 것처럼 sales.korea@rode슈바르즈.com으로 이메일 남겨주시면 저희가 관련된 내용으로 확인하도록 하겠습니다. 예. 오늘 벌써 5시 12분입니다. 오늘 긴 시간 동안 고생 많으셨고요. 오늘 참석하신 분들 다시 한번 감사드립니다. 오늘 남은 시간도 또 즐겁게 보내시는 그런 날이 되실 수 있기를 빕니다. 오늘 준비한 웨비나는 여기서 마치도록 하고요. 다음번에 또 더 재미있는 흥미로운 주제로 여러분들 찾아뵙겠습니다. 오늘 수고 많으셨습니다. 고맙습니다.